So welcome everyone to the Unblackboxing ExoSphere webinar. We're really happy to have all of you on board today. So I'm Clarissa. I'm the marketing product manager. I take care of ExoSphere and all the marketing related stuff. We also have here our chief product officer, Hemant Chaurasia. That will be one of our speakers today. And also our senior geophysicist, Tim Jones. So they are really the experts that are going to be doing most of the talk today, but I'll be the moderator. And then I'm also going to be opening for questions at the end. So please don't be shy. We are here to really have this conversation, answer any questions and any points of doubt that you guys might still want to address. So just to give a bit of context why we are doing this, a few months ago, we have done a customer survey and a big campaign to really gather feedback on ExoSphere and the things that we could improve on the product. And one of the things that we really heard from clients and from the industry in general is that people really wanted to understand how we get to the final 3D model. So what are the steps, how we get to that final point of the product. So what are everything that is happening in between. So that's why we're doing this talk today, to address all of those points and really explain them in more detail. And I really would like to start with this. I know it's a very technical point and it's quite a technical product and new technology. So we want to address all the equations, the mathematical modeling and everything in between so that you guys can be an expert by the end of the talk. But no, not really, don't worry. We know it's a bit complicated sometimes, but we want to make it as simple as possible for you. And I'm not a geophysicist myself, and I can still understand, what's going on and all the concepts behind what we do. And that's the idea that we're trying to do here today. So some parts will get a bit more technical, but we're really trying to do the more that we can to make it digestible for all of you. So the question that we're really trying to solve today is, how do we generate the 3D models and how we get to that point? What are all the steps and kind of maybe the things that we thought that were kind of boxed and not really spoken about before, but we really want to make this a transparent conversation and a transparent process so everyone really understands what is going on. So we're going to cover a few topics to really get a better understanding of the whole product, including how it works, how we collect the ambient noise tomography data, the geode, which is our satellite-enabled node, and the edge processing capabilities that we have, the monitoring in real time connected to the satellite, the inversion approach, that is kind of the last step that we do, and then the product demo. We're going to do a quick product demo and we're going to be announcing 3 new features. So today is the official date for this announcement. You guys are the first ones to know about it. So we're really excited to announce them today, and we're going to give you a sneak peek of how they work and how they look in the platform as well. And then we're going to open for Q&A at the end. So don't be shy to ask anything that you'd like. Just to give a bit of background about Fleet for the ones who don't really know much about us. Fleet was founded in 2015 as a tech space startup to really launch satellites and connect critical industries. But one of the challenges that we had is, what are we going to connect? What are like critical things that we need to connect to solve world challenges? And the critical minerals were happening kind of at the same time, with a lot of pressure to hit the net zero priorities. So it was something that really called our attention. And we thought, well, there are not many geophysical models and methods that can really solve this problem with like speed, with good depth to see underneath the earth, to search for the new minerals and new deposits, and also that can do that in a cost-effective way. So we really decided to develop this product in-house to meet that challenge. And now we have 100+ employees all over the world with 30+ nationalities, including myself. So it's been a very exciting journey. And one of the challenges that we had is to obviously really grow our geotechnical team in the geophysics space and the geology space to really support the product, support the clients, and really deliver the best that we could to solve those challenges. So now we have experts in the US, in Canada, in Australia, and it's ever growing. So we're really happy to have all of them on board. And I'm sure that some of the clients that are here today, you know, some of them, and we are always in touch. And it's really good to have all of them working with us. Up till today, we have done 150 surveys worldwide in 5 continents. So we have also key mining clients worldwide, and it's been really, really good to work with all of them. And it's a very exciting journey. So now I'm going to pass the word to our Chief Product Officer, Hemant, and he will be covering some of the ExoSphere topics with you. Enjoy the talk.
Thanks, Clarissa, and thanks everyone for joining. Wonderful to see a number of familiar faces in the crowd, clients, and for everyone who's a bit newer to Fleet and to ExoSphere, I thought I'd start off with a little bit of the high-level explanation of what exactly happens when you do an ExoSphere survey. How does it work at the highest level? And then after that, we'll go into the details. So, at the highest level, ExoSphere is a new 3D velocity dataset for exploration. Something we're very proud of is our ability to image undercover with depths up to 2.5 kilometers, and how quickly we can do that. You'll see as we explain everything here. Oops, sorry. You'll see how everything that we do is really optimized for speed. And in particular, we use the space tech part of this is satellite connectivity to every sensor in the field that allows our data to be real time. And the other important point about ExoSphere is the very low impact that it has when it's in operation. As a passive seismic method, we can very easily and quickly do this with basically leaving no trace on land. So this next video is a little bit of a sketch showing how this works. So first off, we start with exploiting the ambient seismic noise that is everywhere. And in every survey that we've done, we're leveraging the ambient seismic noise in the earth. Tim's going to tell you more about that. But at this high-level explanation, what we're really doing is using our geodes to measure that ambient seismic noise using an onboard geophone and 2 other important elements. We have onboard edge processing electronics that process that data in situ on the device, and a battery-powered direct-to-satellite modem on every device, so that when we deploy these geodes in an array across an area that a client would want to explore, they would make their measurements and send their data back in real time via satellite. That goes directly into our cloud platform. And what we do then in the cloud is we apply our own very, very optimized for speed data processing algorithm to apply the ambient noise tomography technique and produce a 3D seismic velocity model of the subsurface. And the real, how quickly we can do it and how deeply we can explore. So I mentioned a couple of kilometers down, and we can do that in a matter of days, from starting a survey to actually delivering a model result. Click to the next one. There we go. So in that explanation, I mentioned, oops, sorry. In that explanation, I mentioned how we are generating 3D models using the recorded data from the geodes. The rest of this talk is really to unpack that step. And so at the highest level, we would boil it down into these 5. And we're going to talk about every one of these in more detail. So first point is leveraging ambient noise and understanding everything about it as our natural probe of the subsurface. Step 2 is to record that time series, as you saw with the geode, exploiting the edge processing we have on board and the satellite connectivity. Step 3 is that we use that setup to monitor this survey in real time. This is where the space technology comes in and where we're really solving for speed and to make this a dynamic exploration experience for the client. Step 4 is what we immediately do with that data is generate 2D maps of this seismic wave velocity using by processing the data And it's 2D maps that we could call 2D phase maps for different frequencies of seismic noise. And then how this becomes a 3D model is this last step on the right, where we exploit the physics of this ambient noise, which is that different frequencies sample different depths. And we use that to produce a 3D model by inversion. So at the highest level, I want you to think of these 5 steps as kind of the framework. And I'm going to hand over to Tim, our senior geophysicist, who is very much the expert, to walk us through more of the finer points on each of these. So over to you, Tim.
Thanks, Hemant, and thanks, Clarissa, for the introduction. So the first thing to mention is that there are a lot of different applications for this ambient noise tomography. Using this technique, it's really given us our sort of first order picture of Earth structure. So we can image very deep down to the core. And so giving that whole Earth picture has really come from this ambient noise tomography technique, as well as some other techniques that we use in research. I can use it for earthquake assessments, urban seismology, environmental monitoring for things like landslides or volcanic activity, a little bit of oceanography. But the area that we're really focusing on here is using the technique for mineral exploration. So there's a lot of different scales and a lot of different applications just here. So why do we target this ambient noise signal? Well, one reason is that active sources are expensive and they can be environmentally invasive. Passive sources, on the other hand, are freely generated by nature and other kinds of human activity. So things like the wind rustling the leaves of trees, or the ocean, trains, roads, cities, all these things make up the source that we use to build and construct our 3D model with. The other reason is that data collection is really simple. You can just deploy and record using these geodes. You don't have to sort of plan what you're doing with large fiber-sized trucks or anything else to generate an active source. You also, because of that ease, you can deploy it over very large areas very quickly. One of the other important points that will come in a little bit more when we talk about the inversion, and Hemant mentioned it before, was that seismic waves, seismic surface waves, are dispersive. So the wave that we're measuring here is the surface Rayleigh wave, and it has this kind of propagation. The fact that these kind of waves are dispersive essentially means that different frequencies are sampling different depths. So we can do an analysis that kind of takes those different frequencies and gives us a more robust inversion in terms of depth. Unlike other maybe potential field techniques where you can't do that kind of analysis, we can get the solution here to be more unique. So taking a look at this kind of typical seismic recording of an earthquake in Brazil, magnitude 6.8, you can see this little spike here. That's the impulse response due to the earthquake. Following that, there's a package of waves called coda waves. That's that impulse response as it's now kind of rattled around in the lithosphere and bounced off multiple contacts and kind of been pretty busy giving us this messier signal. But what's important here is that most of the time when we're recording, we're just recording the ambient noise. So most of the field is kind of dominated by this ambient signal. So it's really important that we kind of ask the question, well, how can we then use this signal that's always operating, that's everywhere, to image the subsurface? And part of the answer is this process called cross-correlation. So what happens is we measure this kind of messy signal at one station, we measure it at another. And what we want to figure out is how long did it take the energy to get from one station to the next. And then we do that is by this process called cross-correlation. We essentially slide one wave field, one waveform past the other, and we look for the time at which those signals are most similar, where the overlap is best. And it's this cross-correlation function that you see here in the bottom panel that peaks when we get that overlap. And so here it's at around 100 seconds. That 100 seconds is the lag time of the wave to get from one to the other. So we know the distance between the receivers because we put them out. We now know the lag time we can get to velocity. We then make those measurements pairwise across the entire array. So every geode forms a pair with every other geode. So when we add one, we get this exponential kind of increase in the number of measurements we can make for every geode. So you can see here are the receiver locations. This is just for 16 receivers, and these are the ray path coverage you get from that kind of setup. And it shows how you get a very dense measurement setup just with 16 geodes. Typically, we would deploy something like 64 or 100, so that density really increases, and we get a lot of coverage over the area, and end up with many measurements. And that's key to building up those phase maps that Hemant talked about earlier. There's a bit of a challenge with this passive noise data, and that's that you have to stack the data in order to distinguish signal from noise. And the amount of stacking, the amount of data that you need, really varies location to location. So the kind of traditional approach to that problem is to just leave the receivers out for a conservatively long period of time, because it's sort of more costly to not collect enough data and kind of fail in being able to construct a model than just to leave them out a bit longer and kind of continue collecting. But if you look at the example here, the peak in this growing signal to noise ratio curve occurs in under a day. So in that example, that would mean up to 13 days of excess collection. On average, we see something like 3 to 5 days. But the point here is that you don't really know how much data to collect. So Fleet's solution to this is the real-time geode. So it's a purpose-built geode to send the data direct to satellite so that you get the data in real time. That minimizes collection times and allows you to do some early QC, QA on the data. The geodes also act as this kind of distributed computer in the field because they have a CPU on them that allows them to do some edge processing. If you look at the typical kind of collection times as a comparison, the traditional sensors have this fixed period. So it could be 10 days, it could be 14 days, whatever it is, it's a single point at which we want to take them out of the ground. The geodes have this optimized collection time based on a real-time analysis of the data. So maybe 3 to 4 days on average. For one survey, maybe that's not a big time save, 10 days or so. But if you start to collect more and more surveys, down here, the example is 10, the difference becomes really big. So this is kind of allowing our clients to get their data sooner, make decisions sooner, and also ensure the data is of high quality. So what about this edge processing component that I mentioned? What we mean by edge processing is just processing that happens on the edge of the entire workflow from measurement to 3D model. And so it's happening here on the geode. The kind of processing that we do is just standard ANT processing steps that help accentuate the kind of most useful frequencies of the spectrum and help remove unwanted signal. So why do we do these on the geode? They help us get the data back faster by compressing it. So they kind of are standard ANT processing techniques that have this added benefit of compressing the data to get through a bandwidth limited satellite network. And the main step that actually permits that is something called 1-bit normalization. So you can see on the top panel here in blue, we have this raw data signal that contains the amplitude and the sign of the oscillations of the wave. The 1-bit normalization compresses that by 32 times. It essentially removes the amplitude signal of the wave and just retains the sign. So that's what allows us to compress the data to a quite small amount. But it is kind of pretty commonplace in ANT processing. The important thing is that these 1-bit noise correlations have the same phase as the raw data correlation. So the peak here that we can see still occurs at the 100-second interval after we've done this processing step, the same that we saw earlier in that raw data cross-correlation example.
Awesome. So the next part of this, thanks, Tim, we're going to talk a little bit about the real-time quality control, so that third step. This is where we're really exploiting everything that Tim has just described about what we have in the geode, this real-time connectivity. And in the ExoSphere platform, as a client operating a survey, this is an example of what you might see. You get a real-time survey dashboard where you get to see data coming back from the survey in real time. In particular here, this is a view that's showing battery levels and device health. This is very useful operationally in that anytime there are issues with devices that they're immediately seen and can be immediately addressed. You don't lose any time, don't lose data. And you're seeing here as well the beginning of looking at real-time quality control of the actual survey data itself. In this view, you're seeing an overall measure of signal-to-noise ratio. But on the next slides, we'll talk about that a little more. So one of the things that you definitely will get out of this survey dashboard, oops, sorry, a little bit, there we go, is noise conditions. From this real-time feedback from the sensors, we can assess in real time the ambient noise conditions at the survey. Here's an example of a beamforming plot that we use internally to assess the directionality of the noise and the magnitude of the noise, frequency content of the noise, and all of these things are important to understand for how the model is generated, and also they're actionable in terms of the array geometry. So if we see issues at this point, we can, in the next move of the array, account for that by reorienting the array in the right direction. We can also adjust spacing of the array to account for what we've seen in the noise conditions. And we get that feedback during the survey instead of weeks after the fact. The second aspect is signal to noise ratio. And so that's another, Tim was talking about correlation functions, cross-correlation functions, and signal to noise ratio. We actually get that feedback in real time during the survey, in that we're getting the data from the geodes. We're able to compute these in the cloud during the survey. And so we can see where we are. We can see where we are on signal to noise ratio overall. We can ask, is it high enough to call it at this point and construct a model? Has it reached peak value? And in general, this is really the value proposition of speed, is knowing when we've got enough data and we can quickly move on to the next survey area or the next survey objective. And then the last point here is that we actually we can form a preliminary model during the survey. And this is something that we can use to understand, okay, are there any, it's maybe not the final model, but do we see some areas of interest that we didn't expect? And if we do, there's an opportunity there to dynamically adjust the survey as you go. So if there is some feature appears on the edge of the survey, then we can, in the immediate future, move the array more in that direction. If we see a structure that has a strike, we can follow that strike in the immediate next hop of the survey. And together, these are all the things that add up to a much more dynamic exploration experience enabled by this real-time monitoring. So now let's zoom forward to, we've completed the survey and we're working on a final model, and I'll hand back to Tim to tell us about the inversion step.
Yeah, thanks, Hemant. So what are these inversion methods, and what kind of problems do we apply them to? So broadly, science relies on this feedback between prediction and observation. And so classically, you might construct some model, get some predictions out of it, and then test those predictions against some observations or data. Inverse problems go in the other direction, and they begin with data, and they seek to look for models that best explain that data set. So an example of an inverse problem would be you see some footprints on the ground, and you want to get to the animal that created them. Going in the other direction, you start with the emu, and you kind of want to figure out, okay, what would its footprint actually look like? Now, these problems are sort of everywhere in science, and they're particularly ubiquitous in geophysics, because we're sort of in this situation where we can only get indirect measurements of the subsurface. So we're sort of confined to what's happening at the surface unless we're doing downhole drilling. And that kind of indirectness sets us up for needing to use inverse methods to get that image of the subsurface. So for gravity and magnetics and electromagnetic techniques, you're all going to be using these techniques if you want to go from that 2D grid into a 3D model. The inversion approach that we take with ExoSphere has two basic steps. The first is that we construct these 2D phase velocity maps for each frequency. And again, it's important to note that those frequencies are sensitive to different depth ranges. That's what gives us a kind of robust solution for the depth inversion in the next step that essentially allows us to accurately place objects vertically. Comparing that to potential field techniques, you have this higher degree of non-uniqueness, where you can sort of place objects anywhere you like vertically and just change the magnetic susceptibility or the density of that to kind of get the model matching the data. Here's an example on the right-hand side of two phase maps for different frequency for a survey. You can see here at the lower end, we're detecting these longer wavelength features. You can already see some structure coming out of them, some north-south structure. Moving up to the higher end or the moderate part of the frequency spectrum, at around 5 Hertz, you start to see smaller scale refinements, little features in that model that are coming out closer to the surface. So the second step is that we invert for the optimal 1D velocity structure for every cell in the model to construct the 3D result. So in this search, we're looking for velocity and depth interfaces that best match the data through an optimization framework. There's also this third sort of optional step where we can reduce the uncertainty of that final result with additional outside data. So we know that geophysical techniques, that inversion techniques lead to non-unique results, but we can reduce the search space by including additional data that our clients have. For example, here, drill logs, we might tell the inversion or guide the inversion to say that there is some interface between some depth range, or we might block out parts of the velocity search space entirely by recognizing that lithologies that we see in those drill logs have to be within a certain range. And then we can update the model and get something that is a more robust solution that has a reduced uncertainty value. So that's it for the kind of final product that we deliver. I'm going to hand back to Hemant now, who's going to give a bit of a recap and go into live demo.
Thanks, Tim. So coming back to where we started here, the 5 steps, you've heard about them now: how we use ambient noise, how we record the time series for the geodes and edge processing, get that data back, monitor in real time, generate these 2D phase maps, and then exploit the physics of dispersion to generate this 3D model by inversion. This is really the overarching process, and hopefully you've taken something away with this from this great explanation that Tim has provided, looking under the hood. One way to wrap this up, I think, is let's look at an example model just to show you what an end product looks like. So here's an example of an IOCG deposit from a recent client survey. And this is how it shows up in our platform. And you're really seeing 3 things. I think first you're seeing depth. Here we're seeing, in this case, resolving to a depth of about 1 kilometer fairly effortlessly. And this is really an advantage in lots of cases where we're exploring undercover. The second thing that you're seeing is speed. This is a model that we went from deploying the sensors in the ground to having a model like this in days versus weeks or months. And that's really leveraging everything that you heard about the technology and the processing approach. And then the third thing you're seeing is that this is very much a 3D model that's just revealing 3D structure. And in this case, at this site, we're seeing the ANT model maps granites on the east, it maps volcanics on the west, and bounding the mineralized zone of interest. It shows gabbro intrusives that are interesting to this particular client. And in particular, it gives them a way to explore areas that they haven't historically been able to look at. And it's something that's very useful for that client. So all in all, it adds up to a fast and deep exploration experience that nobody else can deliver in this way in 3D. And our whole team really loves delivering this experience to clients and exploration teams. So next slide here, we'll maybe pivot to a bit of something else, like a bit of a bonus topic. We're here today also announcing 3 new features that are really in the spirit of this talk, actually, where our goal in this talk is that hopefully you come away understanding a little bit more under the hood of ExoSphere. And these 3 new features are on the same theme. They're to help you understand, give you transparency and understanding of all the models that you create in ExoSphere. So there's 3 features. The first 2 we're calling the source data pack and data processing report. So these are 2 new deliverables that will be available automatically in the platform for any currently in progress or future survey. And here I'm showing you on the right where you get that, so alongside where you download your results. And the source data pack is really, it's a package of all the raw ingredients to produce the model. So Tim mentioned the 1-bit normalized data or the edge process data set that comes back from our geodes. That's what this file is. It gives you that raw data in your hands directly, together with the computed cross-correlation functions. So you have the raw ingredients for the model as a digital asset on an ongoing basis. The complementary part of that is the data processing report. And the data processing report is something that is also available on demand in the platform for any currently in progress or future survey. And it's an automatically generated report for your model. It includes 14 different plots that are, in this case here, you're seeing on the screen, diagnosing the noise conditions at the site as recorded in your survey. It'll tell you about the frequency content, some of the things we talked about earlier, and it gives you some explanatory narrative on each of those plots, aiming to make this understandable to anyone. You don't have to be an expert geophysicist to understand this report. This report also includes the actual inversion parameters that were used to generate your model. So in practice, what this, together with the source data pack, these two deliverables are make the survey into a digital asset that you can keep for years and years. You could reprocess yourself if you wanted to, because you have now in your hands everything that was used to create the model. Then the third feature that I'll say a bit about is our first quantitative measure of confidence in the model, and we're calling this one sensitivity. This shows up now in the platform, again, for currently in progress and future surveys. And here I'm showing you how we visualize it in the quick viewer online. It's really a measure, it's a relative measure of how much the geode array has sampled each 3D part of the volume. And so darker areas in this view are less sampled. And so that's a quantitative indicator of the likely model quality and resolution that you could expect in those parts of the model. We give you a few different ways to visualize that in the cloud as well. But just like you download results, you can get this same quantity in the results set automatically included. In the platform, this is all explained. There's an FAQ to give you a bit more detail on how this is calculated. But fundamentally, it's a measure of confidence. It's our first measure of confidence that we're giving you quantitatively in the platform. Altogether, these three features, we really hope that you find value in them. It is our attempt to make the models even more understandable, transparent, and insightful for your exploration programs, and we hope you put them to good use. So back to you, Clarissa.
Thank you, Hemant. Thank you, Tim. That was great. So yeah, so those were the announcements that we're really excited to make today. We're gonna be sharing more info about them, but at least you can ask us any questions firsthand if you like. I'm gonna open up for Q&A now, and you can please send the questions on the chat. I got one question here that we've received beforehand that I would like to address and to begin with while we wait for the other ones. So the first question is, what is the general rule of thumb for resolution and spacing? So maybe Tim, do you want to tackle this question maybe?
Yeah, sure. Do we have a slide for this, a visual?
Yeah, we've got it.
So yeah, the resolution estimate is about 10% of the depth or 20% of the geode spacing. The reason why we call it an estimate is because ultimately resolution depends on the best resolution depends on the shortest wavelength that you're able to measure. So it's something that actually comes out of the analysis as we're recording the data, and that we can update once we start getting some sense of what the noise conditions are. So this kind of puts us in the ballpark for where the resolution is going to sit. And then once we get a little bit more information that's kind of site specific, we can be more precise about that resolution.
Okay, great. We also received another question on the feedback form from Paul, and the question is, when do you plan to integrate gravity measurements into the geophones? So maybe that one for you, Hemant.
Yeah, and thanks for the question, Paul. It's a good one. You're pointing out a really important part of our product roadmap, which is really about combining different different types of data with our ANT to augment the model and make it even more useful as the insight into the subsurface. So gravity, it is definitely a logical next step. Near term, our first step is actually to better combine client-provided gravity data in our inversion process and provide a better constrained 3D model that way. We've already done this experimentally for some clients, And you can expect to see that become a more standard feature in the coming year or so. We also have plans to directly capture gravity data with our geode alongside seismic measurements. That's more of an advanced R&D effort on our end, with the teams hard at work at it. It's currently in early stages, and we're targeting approximately 2025 for more general availability of that feature. But basically, as we're working towards this, we definitely welcome conversations with any exploration team that's interested in partnering to shape that capability for their own needs. We definitely want to make it the most useful thing possible. So please reach out anytime.
That's great. Thank you, Hem. We've got a few questions from Ben Peterson. So first one is, can you say more about frequency versus the depth of imaging? Does this technique use only Rayleigh waves? And what is the cell spacing between the nodes? Well, you've already covered some of that, Tim, but if you want to give some more details for the other ones, please.
So yes, we're using the information just from the surface waves, from Rayleigh waves specifically. The maximum depth of imaging is dependent on the longest wavelength that we can measure, which depends on the furthest spacing of those geodes. So another good rule of thumb is roughly a quarter of the furthest spaced geodes is about the depth that we're going to see quality information. So if we're sort of have the furthest spaced geodes at a kilometer, then about 250 meters is the kind of depth penetration we can expect before we actually see the noise conditions of the site. I can see these asked another question there about the cell spacing between the nodes. So yeah, the cell spacing, again, we might sort of nominally set it to about 20% of the station spacing. And then once we get more information about what kind of frequency content the noise has, we can adjust the cell spacing to actually capture the smallest resolution we have available.
Great. Thank you, Tim. And thank you, Ben, for your question. So we have another question from Andy. Thanks, Andy. So it's a bit more about the waves. So how do you discriminate signal, given that you could have any number of the following ambient noise sources? So PS, refracted waves, peg-leg multiples, and directionality variables. How do you offset any potential seismic sources with respect to the receiver layout?
Yeah, so I guess he's asking a number of things, which we do have some slides there that kind of get to the bottom of it. Can we go back to the slide deck, Clarissa?
Yeah, sure. I'll give you control, and then
So yeah, the variable directionality is an important point. If you kind of compare this active source setup, you might have a source here and a receiver here, and the wave comes directly in line, the first arrival. For random sources, or for the ambient signal, we don't actually know specifically where the wave is going to come from initially. So in this example, you might have a source here on the right-hand side. It arrives at one station before the other. So we do that cross-correlation procedure, and we end up with, we end up with this impulse response here that kind of measures that time lag, like I mentioned before, with cross-correlation. Sorry, just having a bit of trouble controlling the screen. Okay, so we can then add more and more sources from different directions. We end up with this more complicated waveform that we have here at the surface. If we keep recording and we keep stacking the data, and this is the purpose of the data stacking, is that what happens is that in the short term, that wave becomes more and more complicated. But once we collect enough data, what we see is that all the other directions that are apart from the one parallel to the inline station direction result in this destructive interference. So all those sources kind of end up cancelling each other out. And what we're left with is the lag time at the beginning and the end of this waveform. That is the sort of correct lag time for the energy that traveled from one receiver to the other. So that's, in a nutshell, how we deal with that problem of directionality in sources.
Great, thank you, Tim. That was handy to have those slides to have a bit more background on how we do that. So we have another question for Tom. Thanks, Tom. So do you envision using ExoSphere in the fields of archaeology for finding subsurface structures or before construction works to search for other things?
Yeah, that would be cool. Hemant, did you want to tackle that one?
It would be cool. Yeah, I think I love the question. There's definitely many other things we can do with ExoSphere than what we're currently focused on niche number one. But in this case, I think some of the challenges are if those features are extremely shallow, like if they're in the first 5 meters of the surface or something like that, that's less well suited to ExoSphere. But maybe Tim, I wonder if you have thoughts on how you would look very close to the surface.
Yeah, so it kind of goes back a bit to the question of resolution and what depths we're sensitive to. So I don't know what kind of archaeological features you have in mind, but sort of at the best end of what we've been able to achieve, about 20 meters resolution. So as long as you're kind of in that sensitivity range, we can give the technique a try for that specific application.
Yeah, agreed. And this kind of ties to one other question we got in the pre-registrations, which was about off-Earth applications. Maybe we cover that one as well. So we actually do think about how to apply all of the same technique on other planetary bodies in line with our mission of exploration. So we actually Fleet has a contract to deploy a version of our geode on the moon. It's called the Demonstrator Grant. The device has a cool acronym that adds up to SPIDER. And in that case, we'll be taking seismic measurements as a pathfinder towards exploring for water in the lunar regolith. So just to give you an idea of this, the spectrum of applications in the future is probably quite wide.
Yeah, that was a good one too. I'm glad we tackled that one. Thanks, Hem. So we've got another question here from Jeff. So he's curious to know if there are any examples where we have done more regional scale surveys over large areas, and if the technology is more suited to small scale or large scale deployments. Maybe Tim?
Yeah, so the technique is sort of, prior to this scale of application, it really was mostly used for big regional lithospheric scale studies. So we can definitely, the technique definitely has the capability to go to that scale. Most of our clients aren't interested in that kind of very, very large scale feature, but we do these big rolling arrays covering hundreds of square kilometers, just in much higher resolution than you might expect, depending on what you mean by the term regional. But for me, I guess I'm thinking regional is like the thickness of the lithosphere, sort of depth of investigation. We can cover quite a bit of ground, and so far our experience is that people have wanted to put the nodes out at about a kilometer spacing. So with 100 geodes, we're covering a very wide surface area and picking up a lot of those regional features, but maintaining that higher resolution for sort of exploration aim.
Yeah, and worth noting that we have clients that are using the array exactly that way, that they'll make use of the fact that we know exactly the right amount of time, the minimum amount of time to collect data in a given position, and then immediately leapfrog to the next spot, and use one array in a rolling way.
Yeah, that's a really good point, Hemant. And I should also say that when we do those big regional surveys, one of the benefits is just to zoom out and get that big picture of the geology, and then we can zoom in with the benefit of the dynamic deployment and sort of downsample those areas that you think are sort of geologically uninteresting, and focus the sampling on those areas that we think are interesting, or we think are going to give us clues into mineralization. So yeah, capturing those scales is sort of inherent part of this real-time deployment aspect.
Thank you. So we have another question here about petrophysics and rock types, which is very interesting, and how the velocity constraints could work best for this type of surveys.
Yeah, so the petrophysical constraints can be really, really helpful. We have to do a little bit of trial and testing, because we know that measurements made on a small scale aren't always going to scale up to the size of the what we're actually capturing with the frequency range that we are with ANT. But reducing that velocity search space is super helpful in providing a more unique solution to the inverse problem. So collecting petrophysical data, if you have petrophysical data, is super helpful for us. Even if it's not velocity data directly, it could just be density information. Essentially from the geophysical eye view, rocks are just collections of minerals, and what's important is, do those minerals result in something that's going to give us some kind of physical property contrast? So not only in constraining the inversion, but it also gives you some insight into whether or not the contrast is high enough to be worth investigating using the technique. Yeah, what we find is, in terms of seismic velocity, if you have sort of handheld velocity measurements, then a minimum of sort of 5% contrast, and we can detect that using ANT. Or if you're looking at density contrasts, about 5 to 10% kind of gives us a better a range to know that we're going to get some kind of physical property contrast that ANT is going to detect.
And maybe I would add that if this data is done before the survey, is even better, because it means that you're really maximizing all the data points that you have already done for an area, plus ANT. So you're actually having a better model. So it will be, the idea is that we really have different methods, we add them to the platform, and then we'll create even a better model and more complete one in the 3D dimension. So that is ideally the best case scenario that you could have from an ANT data set.
Sorry, there's probably one other point to make here, which is that the size of the body really matters too. So the bigger the body, the lower the physical property contrast has to be, because the seismic wave is able to spend more time in that body, and so it's more sensitive to the smaller contrast that's there. The smaller you go, the higher that physical property contrast would have to be to be detectable.
Yeah, great point. Well, let's move on to another question. We still have a few ones here to cover. So one question from Andy. So he's asking about the AI aspect of the product. So does the processing is used to perturbate the subsurface velocities with many different realizations in an attempt to come up with a time and amplitude section that matches the actual subsurface and the data? So maybe Tim, do you want to tackle that one?
So there is a part in the processing workflow where we use these Monte Carlo techniques to kind of randomly vary parameters to essentially search the model space. That doesn't involve any kind of AI or machine learning. Where we're exploring those kinds of avenues is sort of derivative products on top of the ANT data set.
Great, thank you. Another question now about frequencies. What is the lowest frequency of the geodes, and what is therefore the maximum depth of penetration if you spread out your array accordingly? This question from Stefan.
Yeah, great question. The lowest sampling, so the lowest frequency that we can sample is down around 0.1 hertz. The depth that we're going to get there sort of depends on conditions of the geology. So the maximum depth of penetration that we're going to get, yeah, I don't have a specific number for you there. The kind of the typical of what we sample is more close to at the lower end, about 0.3 hertz. And the deepest kind of surveys we've done so far, around 2.5 kilometers in terms of a practical direct experience of what we've measured. Not sure what the theoretical limit should be, but that's something I can get back to you about, Stefan.
Yeah, that's another point. If you have already an area or, something in mind, we are happy to do a feasibility study and provide more technical information on how the spacing, how the depth, and everything else, how it would go. So feel free to be in touch with us with more details, and we definitely will be happy to help. And I think there is one last question here about the geodes. Are the geodes uniformly distributed, or can they be placed randomly in 2D?
Yeah, I like that question. That's a good one. They don't need to be uniformly distributed is the short answer. And so we definitely make use of that. Very often it could be the case that at the project site, there are land access restrictions, maybe some tracks that you must deploy along these tracks, or you must stay along these roads or something like that. And a great thing about the method is that we're robust in that way. We can place the geodes in a different configuration and still create a 3D model. It's sort of an optimization, but we're very flexible in the method itself on the geode placement. We've had, I think, the places where I can recall that coming up, a site where there were tracks as the constraint, another site where we wanted to deploy along roads for convenience, and in both cases, able to produce a 3D model very well.
Yeah, talking about that, we have added a few documents for download if you guys are interested. So if you click on the resources on the bottom tab of Zoom, there's a resources button. And then if you click on that, and then if you click on documents, there is one technical paper, one case study that we have done with Northern Star, with many images on how the deployment and how the 3D model went. There's another shorter case study on copper, a bit less technical, and there's also another document there for you, so feel free to download. Are there any other questions, any other points? Last chance to ask the experts today. Yeah, another question here. So as you were mainly dealing with Rayleigh waves, are the ultra low frequencies affected by ground roll noise? For example, below a certain frequency, low frequencies are too noisy to use? The question from Wei.
Yeah, so at every frequency range, there is some influence of noise, and that's the process of sort of filtering that we do to kind of clean up the data and make sure that we're using signal that is above a certain threshold of quality. The sort of noisiest part that we have to deal with is usually at the higher frequency and the lower frequencies, while we have kind of some of those noise filtering processes to deal with, they're just less complicated.
Great, thank you, Tim. And one last question from Andy. Tim, what is the upper frequency of the geode bandwidth?
So they have a sampling frequency of 20 hertz. So then Nyquist frequency puts the upper limit at 10 hertz.
Yeah, it's a pretty broad range. Yeah, good. Any other questions? Thank you for sticking with us to the end. That is really good to see. So maybe we have covered everything today. Thank you so much for joining. We hope this session was helpful and hopefully answered some of your questions. Don't hesitate to be in touch with us if you need anything else or any other points, or if we can help in any other way. And we just have added a feedback form in the end so that we know how useful that was for you. And also, if you have any other topics that you would like us to cover in the future, feel free to add in there, and we'll take only one minute or two to give us the feedback, and we really appreciate it. Thank you, and have a good day, everyone.
Thanks, everyone.
Thank you. Bye.
See you in the next one.